Good afternoon, students. Today we are going to discuss about the topic parallel plate capacitor. Parallel plate capacitor. That means we are going to discuss about this parallel plate capacitor. We are going to derive an expression for that. So before that, let us see what is capacitor is. Capacitor. What is capacitor is? Capacitor is nothing but it is the arrangement of two conductors. It is the arrangement of two conductors which are separated by an insulating medium such that which is used to store the electric charge and electric energy. So this device or this system is called capacitor. Again I repeat, capacitor is nothing but it is the capacitor means what? It is the arrangement of two conductors which are separated by an insulating medium. This medium may be air or anything it may be. So two conductors which are separated by an insulating medium which is used to store the electrical charge and electric energy. This is called capacitor. I'll write here. Capacitor is an arrangement of two conductors separated by an insulating medium which is used to store electric charge or electric energy. So this is called capacitor. That means two conductors are separated by a small distance with some insulating medium between them. Then these two conductors which are used to store the charge or the electric energy, this is called capacitor. So here these two conductors may be of different shapes or may be of different size. It need not to be same size or same shape. This conductor may be of different shape and size. This conductor may be also different size and shape. So this is called capacitor. For example, if I take, suppose say this is one conductor. Say this is a positive charge conductor. And this is one more like this. Say this is a negative charge conductor. So keep in mind that capacitor means what? Arrangement of two conductors which are separated by a small distance. And here these two conductors should be of opposite charges. Means if one is positive charge and one should be of negative one. That may, and one more. One is of positive potential and one is of negative potential. Then these two are combinedly called as these two conductors collectively called as a capacitor. So therefore, let us say this is a conductor of say plus Q charge, and this is a conductor of say minus Q charge. It is having a potential, say that is plus V. It is having a potential, say that is minus V. Then what is the capacitance of this capacitor? These two capacitor, that means these two conductors collectively call it as a capacitor. What is the capacitance of this capacitor? Means how much charge or how much electric energy can hold by this capacitor. That is written by, that we know that formula. That is, what is that? Generally, yesterday we have defined a formula. That is, charge on the conductor or on this capacitor is directly proportional to V. Therefore, from that Q is equal to C into V. If you remove this proportionality, we can write some constant, that is C. So from here C is equals to, we can write Q by V. So here capacitance of the this capacitor is given by Q by C. Q is nothing but either charge, we can say either may be negative or positive, and what is V there? V is nothing but either this potential or this potential. So this is called capacitance of this capacitor is given by C is equals to Q by V. So in this way, these two conductors which are separated by some medium, which is used to store some charge on it. See here, we can store this much of charge. Similarly, electric field will start running from positive to negative. That means electric field will be, if the charge on it is more, if you give more charge on the conductors, then more electric field will be produced between this, which we say that more electrical energy is there. So that means here capacitor is nothing but it is used to store the electric charge and also electric energy also. So electric charge and electric energy. So electric charge and electric energy we can store on this capacitor. Okay. So now come to the point that parallel plate capacitor. And here capacitor, here it is represented with some symbolic representation is there. That is like this. This is called fixed capacitor. This is the symbol of fixed capacitor, and this is the symbolic representation of variable capacitor. This is a fixed capacitor, this is variable capacitor. That means its capacitance can be varied. We can vary its capacitance, but it is fixed. So this is called fixed capacitor. Now let us discuss about parallel plate capacitor. We are going to derive the expression for parallel plate capacitor. Let us consider this is called parallel plate capacitor. This is of positive charge. This is of negative charge. This is having a plus Q charge. It is having a minus Q charge. Its surface charge density, say that is plus sigma. It is minus sigma. The area of this plate is like this. Say this is the area of the plate. Say that is A. It is also having a suppose the same area, that is A. These two conductors, which we call collectively as capacitor. This is say these are separated by a distance, say that is D. Now this is called parallel plate capacitor. So now we are going to calculate the expression for capacitance of this parallel plate capacitor. How much capacitance it has to store the electric charge and electrical energy. So we are going to calculate that capacitance of this capacitor. So for that, as we know that in case of we have learned in case of infinite plane sheet we have taken like this. We have taken an infinite plane sheet like this. This is an infinite plane sheet. This is also like that, infinite like this plane sheet only. This is also same like that only. So here two sheets are taken like this. Okay, we know that for this, what is the electric energy? Just beside it means we have calculated, that is E is equal to sigma by 2 epsilon naught, where sigma is nothing but charge density of this plane sheet. Sigma is the charge density, areal charge density divided by 2 epsilon naught. It will give the electric field intensity at this point due to this plane sheet. This we have calculated. So here the same like this only, it will also have a charge density, that is plus sigma. For this it is minus sigma. So here, what is the electric field at the center, at the between these two plates? Means we can say that between these two plates, what is the electric field? Means at this point I have to we have to consider a unit positive test charge. Suppose I have considered a unit positive test charge. For this plate will act some force on it in this direction, that is E plus. Due to this, it will be in that direction. It will also, this is negative plate, this will try to attack this positive charge in that direction. So that means I can say E minus is also, both are in the same direction at this point. Therefore, now similarly, if I talk about the outside the parallel plate, if I talk about here you consider a unit positive test charge. This will repel this, that means electric field at this point will be in this direction, that is E plus, and this will try to attract this, that means E minus will be in this direction. Similarly, if you talk about here at this point, here also consider a unit positive test charge. This positive will repel that positive test charge in this direction, and this negative will try to attract this, because this negative, this is positive, therefore it will come in this direction. This is E minus. So here for this plate, the electric field intensity at a particular point is given by, this is the formula, that is E is equal to sigma by 2 epsilon naught. So at this point also we have electric field is how much, means E is equal to sigma by 2 epsilon naught. For this also sigma by 2 epsilon naught. These both are equal, but they are in opposite in nature, and these two get cancelled. Similarly, here also the electric field, due to this both, will get cancelled at this point also. So from this it is quite clear that outside this plate there is no electric field in this region. Similarly, in this region also there is no electric field. Wherever you take like this only, these two will get cancelled. So anyway, there is no electric field. Here also no electric field. Therefore, only the electric field exists between the two plates only. That is in this space only. Therefore, electric field in between these two plates is given by E is equal to E plus of E minus. That means both are in a same direction. That means I can say that sigma by 2 epsilon naught, and one more is also sigma by 2 epsilon naught. So in this way, if you add, both are in a same direction. So that formula, this formula we have to take the 2 times. For this we have to take. Therefore, this will become 2 times of sigma by 2 epsilon naught. Therefore, E is equal to sigma by epsilon naught. Say this as equation 1. So, electric field between the two plates at any point, if you take, what is the electric field, means E is equal to sigma by epsilon naught. We know this formula. And also, since the electric field is set up between this, that means electric field will be from positive to negative in this direction will be. So how much electric field strength is there, means this much of electric field is there. As the electric field is there, then we can definitely say that a potential is said to be developed between the two plates. Since this is positive potential, this is the negative potential, it will have a potential difference across this. Then what is the potential difference between these two plates? That we can write here. Let B be the potential between two plates. Let V be the potential between the two plates. Is how much the potential is? This much potential. Therefore, we are having a formula. What is the formula? One formula we have. There is a relation between electric field and electric potential. As we have derived, E is equals to, we know that, minus of dV by dx. One formula we have. This is the relation between electric field and potential difference. So here, so if I take a magnitude of that, so we need not to take this minus. So here I am going to calculate the electric field magnitude. in terms of potential. So therefore, between these two, the potential I am telling it as a V, and the distance between these two plates is how much? That is D. Therefore, from this I can write that according to like that formula, electric field between these two plates is given by E is equals to V by D. Potential by distance, potential difference by displacement, so distance. So we can write like this. So here I am not taking minus, I am taking here a magnitude. So E is equal to V by D. Say this as equation 2. So here this is also electric field between the two plates in terms of charge density. This is also electric field expression in between the two plates in terms of potential and distance. Both are equal. Therefore, I can say equation 1 is equals to equation 2. Therefore, 1 I can say that sigma by epsilon naught, which is equals to V by D. Therefore, from this V is equals to, I can write sigma D by epsilon naught. I can, this D will come here. So this is the electric potential. What is the potential between the two plates? Means this much of potential difference is there. So also we can write this one. Since we know that sigma is equal to charge by charge, that here I have taken a charge as Q. So I will take here charge by area. You know that surface charge density is equal to charge by area. Area is nothing but area of the plate I have taken as A, and Q is nothing but it is the charge on each plate. Therefore, from this I will substitute this value here. Therefore, I can write here Q D by sigma is nothing but Q by A. So Q by A into epsilon naught. So instead of sigma, I have written Q by A, D by epsilon naught, D by epsilon naught. So this is the electric potential expression. Say this as equation 3. Therefore, now here our aim is to calculate the capacitance of a parallel plate capacitor. Therefore, from the definition of capacitance, we know that C is equals to Q by V. We know that C capacitance is equal to charge by voltage or charge by potential. So I can write here Q by V. What is V here? From equation 3, Q D by A epsilon naught. So here Q will get cancelled. Therefore, C is equals to, this term will go up. Therefore, I can write A epsilon naught by D. So here, this is the expression for a parallel plate capacitor. So this parallel plate is having how much capacitance value? Its capacitance expression is given by, that is C is equal to A epsilon naught by D is the expression for a capacitance of this parallel plate capacitor. Okay. Therefore, if suppose between these two plates, suppose a dielectric medium, a dielectric slab is placed between this of dielectric constant K. For example, suppose say now initially that is the expression for the capacitance of a parallel plate capacitor. When there is vacuum or only air is there, then that is a formula. If suppose instead of this vacuum or air, suppose a medium is placed. Suppose a dielectric slab of medium is placed. Say its dielectric constant is K. K is for dielectric constant of a given medium. For example, if you take for a water, the K value will be 80. The same for a air, it is 1. So that depends upon the medium, which medium you are placing there between these two parallel plate capacitor. That medium K value you have to add there. Therefore, the capacitance of this parallel plate capacitor is given by, say that is, now I am telling a new capacitance, say that is C dash, where C dash is nothing but K times of this value, that is A epsilon naught by T. So here the difference is, what is that initially? C is equal to A epsilon naught by T. This is called capacitance of a parallel plate capacitor when when air or vacuum is there between the two plate capacitor. If suppose between the two plate capacitors, suppose a medium is placed of dielectric constant K, then the new capacitance is given by this formula, that is C dash is equal to K into A epsilon naught by 2. So how much value if you place the K value, if you increasing, that means the dielectric constant of a given medium, if increases, that means the capacitance will be increasing furthermore. So how much time it is generally increasing when compared to that of in air, means it is increasing by K times. It is increasing by K times. Let us divide these two equations, we will get the, we will come to know. See, suppose if I divide these two, suppose C dash by C is equal to, what is C dash means? K A epsilon naught by D whole divided by A epsilon naught by D. So here A epsilon naught by D, A epsilon naught by D cancel. What is left here? C dash by C is equal to K. Therefore, C dash is equal to, this will go there, K times of C. So from this expression, it is quite clear that the capacitance of a parallel plate capacitor when a dielectric slab is introduced between the two plates, then its capacitance will be increased by K times that of the when it is in air. So this is the expression for a parallel plate capacitor. So this sometime it is important question. Sometimes it may ask for 3 months. They may ask. Okay. So here next factors depends on the capacitance of a capacitor. Means what are the factors on which the capacitance of a parallel plate capacitor depends? On what factor does the capacitance depend? That is the asking here. So here very clear from this formula. Here from this formula it is very quite clear that C is equal to general formula. What we got there? We got C dash. Suppose in a medium, if you take K into A epsilon naught by D, this is what we are getting. Since we can also write these two collectively, relative permittivity, or we can write E is equals to PR into E naught. We know this very well, this formula. What is epsilon E means here? This is nothing but this is the permittivity of a given medium. Permittivity of a given medium is equal to relative permittivity of that medium into relative permittivity of a free space. So here in some book they will give as a epsilon R, or in some books they will say with this letter. They will represent with this K letter. That means I can also say this one as a K into epsilon R. Both are same. This is called relative permittivity, which is also equals to dielectric constant also. Both are equal. Okay. So here, instead of these two, I can write this one. This is called relative permittivity of a given medium. So here, these two can be written as like this. So I can write here or I can write this one like this. A, these two will write here. So A epsilon by D. So here factors depends on the capacitance, means capacitance depends on what factor? On what factor? Capacitance depends on what? On what factor? 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 On what That is, capacitance depends on, here very clear that capacitance is depends on what factor? First is area. Area of parallel plate capacitor. That means as the area of the parallel plate capacitor increases, capacitance also increases. Why? Directly proportional. This is one first factor I can see. The second factor I can see, that is epsilon. Epsilon means what here? Epsilon is what here? This is nothing but this is permittivity of a medium. So here capacitance also directly proportional to the permittivity of a medium. If the medium value, that means if this value is increasing, that means if the K value is increasing, means this value will increase. If this total value is increasing, means then I can say that capacitance also increasing. So this capacitance depends upon this value also. So this is the second factor. Now the third one I can say, that is D. And it also depends on the what? That is called distance between two plates. So here, as the distance between the two plates increases, then what will happen here? Capacitance will decrease. That means if this is increasing, this will decrease. So in this way, inversely proportional are there. So in this way, these three are the factors on which the capacitance depends. So these are the factors we can see. So still now we have studied about a parallel plate capacitor. Here, apart from this is very important for our NCERT syllabus, and as well as after this year, two more will come to know that. That is spherical charged capacitor and also cylindrical capacitor. Spherical capacitor and cylindrical capacitor are there. These two are also there. For these two, we need not to derive the expression. We have to just keep in mind the formula for the capacitance of these two. That is capacitance of a spherical capacitor and also capacitance of a cylindrical capacitor. These two formula we have to keep in mind. Derivation they won't ask in an NCERT. Okay, let us draw. I will draw that diagram and I will write you a formula for that. Let us say the first one is spherical capacitor. Suppose say this is a positively charged plate, means sphere. This is also parallel plate capacitor like only. That is parallel plate here. This is called spherical. Means these two are also parallel only. Means these two are having a common center. So this is the sphere of positively charged, and this is having a sphere. This is a sphere of negative charge. Say this is the center. Say this is the distance. Say this is A. The radius of a negative sphere is called A. The radius of the positive charged sphere, say that is B. Okay. So here let us consider. I will take one point. Say this is at a distance. Say that is a distance. Say that is small r. So from here, from this radius, I will draw one Gaussian surface like, or one imaginary sphere. I will draw. This is called sphere or spherical capacitor. This is called spherical capacitor of radius. One is small a and one is of b. So therefore, what is the capacitance of this capacitor? Means the expression for that is given by C is equals to 4 pi epsilon naught into AB by B minus A. So this is the expression for a parallel plate capacitor. So this formula generally we use for solving problems only. They won't ask the derivation for our examination, for our theory examination. Okay, so keep in mind that the expression for the capacitance of this spherical capacitor is given by 4 pi epsilon naught AB by B minus A, where B is nothing but bigger radius, where A is nothing but smaller radius. So this is the expression for it. Similarly, I will talk for similarly we will write for cylindrical capacitor. For cylindrical capacitor also, let us consider this is a cylinder. This is of length, say that is capital L. Say this is an axis which is passing through the center of the cylinder. Say this is of radius B. This is of radius say that is B. Now here I will assume one. This is of say this is positively charged one. This is of positively charged cylinder. Similarly, inside this one more cylinder we can assume. Say this is of radius, say this is small a, which is of negative charge. Same, it is also same like this only. Outer one is positive, inner one is negative. Here also outer cylinder is positive, inner cylinder is negative. Outer cylinder radius is B, inner cylinder radius is A. Here also outer sphere radius is B, inner sphere radius is A. So similarly we can draw same like this only. This is of length say that is L. So therefore we can also assume one more cylinder. Between these two cylindrical surface we can draw. So here say from this axis to this assumed cylinder, say this distance is R. So here the capacitance of this cylindrical capacitor is given by, that is C is equals to 2 pi epsilon naught L divided by log of B by A. So this is the expression for the capacitor of a cylindrical capacitor. So for this we have to keep in mind these formulas only. No need of derivation for this. And here one more thing, you may have a doubt that here one R is there. Here also you have chosen R, but in the formula we won't see any R. Means here, basing on this R, we have to derive. Here there is a derivation is there. In that derivation, we will consider as one assumed cylinder. We will assume first of radius smaller. Then from that we will derive. After deriving, we have to integrate it. That integration, in that integration, we will substitute the value of R as a and B. That means these two are the limits. R has a lower limit, that is A, and R has the upper limit, that is B. So on substituting these two A and B, which is the limit of R, after substituting in an integration by doing integration, and then if you substitute the value of A and B in that R, then we'll get the final answer is this one. So here R won't come. Here R is having a limitation, that is A to B. Similarly, there also, here R is an assumed cylinder, okay, whose first starting limitation is, that is A. Therefore, the bigger cylinder is of B. That means this R is nothing but it is an assumed cylinder which runs from A radius to B radius. So after integrating, we have to substitute the value of A and B in this R. So therefore, after that calculation, we will get this formula. So hence, in these two formulas, we won't get this R value. So finally, the expression for this, for spherical and for the cylinder is this. Is keep in mind, this is for a problem they will ask. No need of derivation. Now come to the point, next topic. So combination of capacitors, that means if two or more capacitors are combined in a series, then what is the effective capacitance? Similarly, if two or more capacitors are connected in a parallel combination, then what is the effective capacitance? Means total or the net capacitance is how much? So there are two possibles are there. One is series combination of capacitor and second one is parallel combination of capacitor. So one after other we'll learn this. The first one is what? Series combination. Series combination. Let us consider that this is the capacitor of capacitance C1, whose first end is, this is called the first end, this is called the second end, whose first end is connected to a battery, say of voltage V, and this second end of a, or the second plate of a first capacitor is connected to the first plate of a second capacitor, and also second plate of a second capacitor is connected to the first plate of a third capacitor, and the second plate of this third capacitor is again, say it is connected to a negative terminal of a battery. So this is the combination. So here I have taken only 3 capacitors. You may take 4 or you may take 5 and so on, up to n also we can take. The process is same like this. Let us see this. Let us consider C1, C2, C3 are the 3 capacitors which are connected in series such that the combination is connected to a voltage V. As here V is the voltage supplying, definitely this volt will be supplied to all these 3 capacitors to drive a charge across the capacitors. So since this is a parallel, since this is a series combination, we know that in a series combination the charge, whatever it is producing the charge which is moving here, the charge will be same in all the 3 capacitors. Let us say on the capacitors will be the charge is, say that is Q, here also Q, here also Q. That means in a series combination the charge will be same in all the 3 capacitors, but whereas the potential will be divided. That means whatever the V you have supplied for this, this V will be used for all the 3 capacitors. That means some amount of this V is utilized to the capacitor C1, say that is V1, which is used to store this charge Q. Here, now in this some more amount, say that is V2 is the potential from the V which is used to store the Q charge on the capacitor C2. Similarly, some more amount, remaining amount, that is, say that is V3 is the potential which is used to store this charge on the capacitor C3. Therefore, whatever you have supplied the potential V, this is used to store the charges on the three capacitors as V1, V2 and V3. Therefore, I can say that from this V, whatever you have supplied is equals to the sum of V1 plus V2 plus V3. Whatever you have supplied is equals to these three. So if you add these three, you will get this one. So we got that. So therefore, here from the definition of a capacitance, we know that C is equals to Q by V. General formula, C is equals to Q by V. So from this I will write V is equals to, we can write, if V is bringing here, C will go down. So I can write Q by C. So this is the general formula we can write. So here V, similarly I will write like this formula for V1, V2 and V3. For V1 I can write here V1 is equals to, here charge is same, Q by C1. So here Q by C1. Similarly for this V2 is equals to, I can write Q by C2. So Q by C2. Similarly V3 is equals to, I can write Q by C3. So here in all the capacitors Q is common, constant is there. So Q is constant. Now V1, V2, V3, these three will be substituted here. Therefore I can write Q by C1 plus Q by C2 plus Q by C3. So this is equals to V. So from this I will take Q as common. If I take, then what is left here? 1 by C1 plus 1 by C2 plus 1 by C3. This is V. So therefore, if I bring this Q here, then I can write here V by Q. If I bring this Q as down, then what is left here? V by Q is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So from here, Q by V means C. Therefore, V by Q means what? V by Q means reverse. Here it is reverse. So I can write like this only. I can write 1 by C. So here I can write this as a 1 by C. So here this is nothing but equals to 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So here 1 by C is nothing but, here C is nothing but the effective capacitance of all these capacitors. Of all these capacitors, effective capacitance. Since these are series, so I will write it as a series. C series. So 1 by CS or CS or C series is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So this is the expression for a effective capacitance of three capacitors when they are connected in series. So this is the effective capacitance formula. So here CS means what here? CS is called effective capacitance of these three. So here CS or C series is called what? Effective capacitance of C1, C2, C3 when connected in series. So when these three are connected in series, then this is called, this term is called effective capacitance in a series combination. So this is the expression we can say. So here one thing is to be noted. What is that? That is here the effective capacitance will be less than that of the least capacitance value in this combination. What does it mean? Here it means that, suppose say this is of capacitance, say that is 1 microfarad, suppose. This is of suppose 2 microfarad, suppose. This is suppose, this C3 is suppose 3 microfarad. Therefore, after substituting these three values here, that is 1 by 1 plus 1 by 2 micro plus 1 by 3 micro. After solving this, we will get C series. C series value will get after solving this entire thing. That reverse it. Why? Because we have to get C series. So we have to reverse this one. So that means if you reverse it, answer will also come that C series, whatever the value finally will get, it will be less than that of the least value. That means in this case, C series, this is called effective. In this case, this C series will be less than that of the least, that is C1. C1 is equal to 1 micro. So after solving this entire thing, whatever the final answer you will get, which is called CS or C series, that C series answer will be less than that of the least one. This is 1. It is the answer will be less than that of 1. So this is the one thing is to be keep in mind. So that one I will write here. This we can say that the effective capacitance in this case will be less than that of the least capacitance value. So least capacitance, whatever it may be the least one, the effective capacitance will be less than that of the least capacitance value. So this is to be keep in mind. This is no. Okay. So once again, you have to, before deriving this derivation, you have two things is to be keep in mind that in case of series combination, charge will remains constant. Charge will be remains constant on all the capacitors. Similarly, and whereas the voltage, it will be divided. These two things is to be keep in mind. In case of series combination, charge will be remains constant on all the capacitor, but the potential will be divided across all the capacitor. This is to be keep in mind. Similarly, in case of parallel combination, it is quite reverse. There, charge will be divided across all the capacitors, but whereas the potential will remain same or constant. So these two, they are opposite. We have to keep in mind. Okay, fine. So here the effective capacitance between the three capacitor is given by 1 by C1 plus 1 by C2 plus 1 by C3. Suppose in this case a n number of capacitors are given, then the same formula we can write 1 by C series is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus 1 by C4 plus and so on plus 1 by Cn. So we can extend this like this up to n number of capacitors. Got it? Now we'll go for a parallel combination. Now the second one is parallel combination. Let us consider here also I am taking a three capacitor. Say this is a capacitor C1, say this is a capacitor, say this is C2, say this is a capacitor, say this is C3, such that the first plate of all the three capacitors are connected to a one terminal as shown in a figure. Similarly, the second plate of all the three capacitors are connected to a one terminal like this. Thereafter, now this first terminal is connected to a positive terminal of a battery, and the second terminal is connected to a negative terminal of a battery. Say this is of voltage V. So as I just now I told that in case of parallel combination, the charge will be divided, whereas the voltage will remain constant. So now it will divide, it will remain constant. So I can say here charge will be divided, but whereas the V, that is potential, will be remains same. So that means here, suppose say V is the potential I have applied across this capacitor, then it will supply some charge. means whatever the charge is supplied by this voltage, so that charge will be distributed to the C1, C2 and C3. Suppose say it has produced a charge, say that is Q. This Q will be divided here into three capacitors. That means for this capacitor, say that is Q1, for this capacitor, say that is Q2, for this, say that is Q3. Where here Q is nothing but the sum of Q1 plus Q2 plus Q3, which is nothing but Q1. Since this is parallel, as I told you, V remains same. So whatever the V you have supplied, the same V will be for this also. Say its potential is V, it is also V, for this is also, say this is V. So therefore, previously V is divided. So that's why in case of series combination, first we have started with V is equals to V1 plus V2 plus V3 we have started. So whichever dividing we have to take first that one. So here what is dividing here? Charge Q1, Q2, Q3 is dividing. So first we'll take here, since first we'll take here Q is equal to Q1 plus Q2 plus Q3. So here charge is dividing. So I have taken Q1 plus Q2 plus Q3. In case of series, then we have taken V1 plus V2 plus V3. Why? Because V is divided. So whichever divided, keep in mind that first you take that one. So it makes you easy to calculate. So therefore, since we know that from the definition, Q is equal to CV, or C is equal to Q by V, or Q is equal to CD, we can write this one. So here Q1 means for the first capacitor, Q1 means like this formula, CV. Here what is there? C1V. C1V. Similarly, Q2 is equals to for this C2V. C2V. Q3 is equals to C3V. So I can write C3V. So in this way, I can write that this formula. So in this case, V is constant. So now instead of this Q, now I will substitute this value here. So I can write here Q1 means C1V plus C2V plus for this is C3V. So from here, I will take V as common. So C1 plus C2 plus C3. So here I can take V as common. That means I will take V as common here. So Q is equal to V into C1 plus C2 plus C3. So if I bring this down, therefore I can write here Q by V is equals to C1 plus C2 plus C3. So here this is getting. What is Q by V? See here, Q by V. If I bring this V down, and what is left here? C I will get. So therefore Q by V is nothing but C only. So therefore C is equal to C1 plus C2 plus C3. So this is the expression for a effective capacitance of these three capacitors when they are connected in parallel combination. Hence I will say this as a CP or C parallel. CP or C parallel, which is called the effective capacitance of these three. That means if the capacitors are parallelly given, then what we have to do? Effective capacitance means we have to add up all the three capacitors, like the C1 plus C2 plus C3. If you add all these three, then I will get the total capacitance of a parallel plate capacitor. So similarly, if suppose n number of capacitors are arranged like this, then we can write like this only. C parallel is equal to C1 plus C2 plus C3 plus C4 plus and so on up to Cn. Like this we have to extend this value. Okay, now here also we have to note, we have to take one note. What is the note here also? Note. Note is to be keep in mind. What is that note? Here the note is the effective capacitance of the parallel capacitor will be greater than that of the greatest value. In case of series combination, the effective capacitance is less than that of the least value. In case of parallel, greater than that of the greatest value. See, for example, if suppose C1 is of 1 microfarad, C2 is of 2 microfarad. Suppose C3 is of suppose 3 microfarad. Then what is the effective of this 1 plus 2 plus 3? That is 6 microfarad. So 6 microfarad means the effective is how much? 6 microfarad, which is greater than that of the greatest value. Here greatest value is how much? 1, 2, 3. 3 is the greater value. So now the effective is how much? 6, which is greater than that of this greatest value. Hence we can say that in this case we can write that the effective capacitance of a parallel plate effective capacitance in case of parallel combination will be greater than that of the greatest value capacitance in this combination. So here the effective capacitance will be how it will be? It will be greater than that of the greatest value. So this is the thing is to be keep in mind. So here what we have divided here? In case of parallel combination, keep in mind that charge will be divided, voltage will be remain same. In case of series, charge will be remain same, voltage will be dividing. So in case of series combination, whichever the divide is there, that we have to take. In case of series, we will take how V is equal to V1 plus V2 plus V3. So from there, this formula V value we have to substitute here. Means V1 is equal to Q by C1, V2 is equal to Q by C2, V3 is equal to Q by C3. Why? Because here Q is constant in case of series. So that value we have to substitute and we have to calculate. Similarly here also. Here the dividing V is what it is dividing here? Charge is dividing. So Q1, Q2, Q3. So from this formula we have to substitute here by making V as constant here. So from this we got this is the expression. So this is the expression for a parallel plate capacitor. So thank you everyone. So here from the next topic we are going to discuss about some important topic regarding this capacitor. On this capacitor some problems are there. How to solve the problem basing on this combination. Here separately we have seen that a series combination we have separately seen, and also we have seen separately a parallel combination also. Suppose in a one circuit they will give, in the circuit suppose like this capacitors are there such that they are the mixture of both series as well as parallel if they have given. Then what is the effective capacitance during that case? That we can learn. By using like this formula only. By using this series and parallel formula only, we can calculate the effective capacitance between the any two ends. So this formula we will learn in the next class. Okay. Till then, thank you everyone. Okay, thank you. Okay.